Good afternoon, everybody. Thanks for coming. I'd like to welcome Sam Hadden here. Sam comes to us from the University of Toronto, the Center for CETA. Gosh, what is its acronym? Canadian Institute for Theoretical Astrophysics. Center. I've known Sam for some time. He has a fabulous piece of software called CellMech. And I'm trying to encourage him to make this available to the masses. So this is celestial mechanics for the masses. All the esoteric celestial mechanics that has happened over the last, several centuries is now packaged into Python, and it's available for everybody. So we're trying to make that actually become reality. So Sam got his undergraduate degree at Purdue, then his PhD at Northwestern, and he was a postdoc at Harvard, and now he's doing a second postdoc at CETA, the Canadian Institute for Theoretical Astrophysics, where he is a postdoc fellow. It's the senior postdoc fellow, they call it, or something.
I don't know.
5-year thing. And I'm very pleased that he's able to spend a few days with us here. So welcome, Sam.
Thanks. Yeah, I'm excited to be here. This is my first time in Tucson. I've had a lovely time so far, and I'm around for a few days. So if anybody wants to meet and chat, just let me know. But for now, and I should say, I don't know what the norm is here, but feel free to interrupt me if you have questions at any point. It's more fun. So today, I'm going to tell you about what I think is one of the most exciting upcoming opportunities in exoplanet science, where for the first time, we'll be able to start probing other planetary systems at solar system-like scales in a way we haven't been able to up to now. And I'll hopefully convince you that by understanding how orbital evolution plays out on these scales, we can go beyond just simply getting demographics of these types of systems and try to say something about how they form and evolve, and also put our own solar system in better context. But before I get to all that, so this year is the 30th anniversary of the first exoplanet discovered around a main sequence star. And perhaps the most important lesson we've learned over the past 30 years is that exoplanets are ubiquitous. In other words, something like an order unity fraction of stars out there host one, often many planets. And our sun is by no means unusual in the fact that it hosts planets. And what's more, we find a very broad diversity of planets out there. This is easy enough to appreciate by just looking at where exoplanet discoveries fall in this plane of planet mass versus orbital separation. We find planets all over this plane, and very frequently in places where we have no obvious analogs in our own solar system. And I and others have spent a lot of their career trying to understand the types of planets that you see here. But I'll be telling you mostly today about how this picture is going to change in the next 10 years or so. And in particular, one of the biggest lingering questions that's probably still hanging over exoplanets after 30 years of discoveries is how unusual or common is our own solar system? Very few, despite all these discoveries, we have very few analogs of our own solar system planets to date. Our planets occupy pretty lonely parts of this parameter space, with the exception of maybe Jupiter. There's not really any analogs for our own solar system planets on this plot. And one might see this and fret that perhaps solar system-like systems and by virtue of that, habitable-like Earth-like planets are cosmic oddities and very rare. But of course, I'm sure many of you are already aware that our principal means of finding planets to date face increasing detection difficulties as you go to both wider orbital separations and lower planet masses. So that up to now, we've been largely blind to anything except for Jupiter around another star. And so us not finding solar system analogs is totally consistent with basically just detection bias. But fortunately, like I said at the outset, that will change in the very near future. So my plan for today is to tell you first about how we can start probing solar system scales, or planetary systems at solar system scales, with microlensing, and then talk about how we can use dynamics to go beyond just getting demographics from these discoveries. And in particular, I'll talk about how free-floating planets can play a big role in that. And then I'll tell you a little bit more about how we can understand the dynamics of planet-planet scattering that leads to free-floating planets. And then finally, I'll close with a brief discussion about clues of our own solar system's production of free-floating planets and how orbital evolution has shaped our own outer solar system. So I'll start with how we're going to start probing other planetary systems at solar system scales. And this is thanks to the Nancy Grace Roman Space Telescope, which is set to launch next year. So this is a wide field near infrared space telescope. It's NASA's next flagship mission. And as part of the mission, it'll be carrying out what's called the Galactic Bulge Time Domain Survey, where the telescope is going to monitor 7 fields towards the galactic center and monitor these fields at a 15-minute cadence for 6 72-day seasons. And for the purposes of planet detection, the most important thing it'll be doing is searching for microlensing planets. And so the basic way this works is that as Roman stares towards the galactic center, every once in a while we'll get lucky and a foreground star will pass between Roman and its line of sight to some background star. And as it does that, the gravitational influence of that foreground star causes it to act like a lens. So its general relativistic warping of space causes it to act like a lens and magnify the light from that background star. And when it does this, it produces this sort of characteristic magnification curve versus time that you see in this animation. If in addition, that star, the foreground star, hosts a planet, the planet's own gravitational influence will modify the lensing properties of the system so that you get this characteristic sort of little bump in the magnification that you see from the microlensing event. And you can take these sorts of magnification patterns and from them back out a planet mass and its orbital separation, or at least its projected separation. And it turns out that this method is particularly well suited for probing planets at distances beyond about 1 AU out to a few tens of AU. So in other words, it's sort of ideally suited for finding solar system analog planets. And if you take what we know about exoplanet demographics based on what we've discovered to date and make some extrapolation, it's expected that Roman should find a few thousand exoplanet discoveries in this regime between a 1 and a few tens of AU and down to as low as about a Mars mass. So this is exquisitely sensitive even to relatively low mass planets. Okay, so that's great. We'll finally be able to say something about how common planets are in this sort of mass and separation regime, analogous to our own solar system planets. But of course, microlensing is a bit strange among planet detection methods in the sense that once you make a detection, you measure a mass, you measure a separation, and there's very little, if anything, you can do to actually follow up and learn more about individual systems. And so how can we go from this sort of demographic census of planet occurrences at these sorts of separations to things we care about, like understanding how these sorts of systems form and evolve? I'll hopefully convince you that we can use our understanding of dynamics to say something more. And a key role in this story is played by so-called free-floating planets. So in addition to detecting microlensing events from stars, any sort of free-floating massive object can act as a gravitational lens, including planetary mass objects. This is basically the same effect that I showed in that illustration earlier, but now instead of a star acting as a lens, you just have some free-floating planet. Of course, we don't observe cartoon planets floating through space, but rather just magnification events. And you really have just one key physical observable for any microlensing event that's connected to the physical properties of the lens, and that's the timescale over which the magnification occurs. And this is sometimes referred to as the Einstein timescale. So it just scales like the square root of the mass of the lensing object. It depends as well on the distance to the background source, as well as the lens and their relative velocities in the plane of the sky. So these will generally not be numbers that we know for typical microlensing events. But if you plug in any sort of reasonable numbers based on what we understand about our galaxy, you find that if you measure an event that's on a timescale of a few hours, it basically has to be caused by a planetary mass lens. And if you look in ground-based microlensing data, for instance, the Ogle survey, we do indeed find these sort of short timescale events. So I'm showing a lineup of a few detections of short timescale events just to give you guys a sense of what this data looks like in practice. And if you carry out a microlensing survey for 9 years and histogram up the sort of event timescales you find, you get something like this. So this is results from the MOA survey, another ground-based microlensing survey. And what you see is this sort of broad peak centered around 10 or 20 days that's attributable to what we understand about the population of stars and brown dwarfs in our galaxy. But then at these sort of sub-day timescales, there's a little shoulder that's basically implies there's a substantial population of free-floating planets. These sort of short timescale events can only be caused by planetary mass objects. And if you turn the sort of statistical crank by asking, given that we saw this many short timescale events, what does it imply about the total population of free-floating planets out there in the galaxy? You get a number of something like 20 free-floating planets per star. So the best fit sort of population model tells us that this is dominated, at least in number, on the low mass end, so that these 20 free-floating planets account for about 80 Earth masses worth of material. But still, that's a lot of free-floating planets. And if you furthermore take this sort of best fit inferred population based on these ground-based statistics and ask what you expect Roman to find, we should get something like 1,000 free-floating planet detections, about half of which come from things lower mass than an Earth mass. Now, where do all these things come from? So it's thought that star formation, or generally understood that star formation can only produce things as low mass as about a few Jupiter masses, perhaps. And so this substantial population of free-floating planets dominated by low mass stuff presumably forms around stars and then is ejected through some sort of dynamical process like planet-planet scattering. And in fact, it's thought that our own solar system early in its evolution might have produced a free-floating planet. So the basic picture, which would generalize to any other system, is that the planets, in our case, in this case, our giant planets, start out in an initially more compact configuration, presumably due to interactions with the protoplanetary disk, causing their orbits to migrate convergently and sort of clump together. At some point, the protoplanetary disk disperses, and it's no longer there to damp down orbital eccentricities that are excited by the planet's mutual gravitational interactions. Eventually, the planets evolve onto crossing orbits, and some unfortunate extra ice giant gets too close to Jupiter and gets chucked out of the system. I should say what I'm plotting here, just because I'll show more stuff like this later, but the thicker solid lines are the individual semi-major axes of the planets, and then the thinner lines are the perihelion and aphelion distance of the planets. So each planet's sort of radial orbital extent is between these two lines. Great. Okay. So one little piece of dynamics that'll be helpful to understand for our story going forward is encoded by the so-called Safronov number. So this is the ratio of the energy required to escape from a planet's surface relative to the energy required to escape from the star's potential well at the star's or at the planet's orbital location. And so planets with Safronov numbers much larger than 1, like Jupiter and our other giant planets, will tend to eject things that they scatter out of our system before they run into them. They can easily impart a random energy to whatever they're scattering through close encounters without needing to have a close encounter closer than their own surface. By contrast, Earth and the other terrestrial planets sit in this regime with a Safronov number much less than 1, and they will generically collide with anything that they cross orbits with or scatter because, again, they need to have a close encounter to impart orbital energy to things that they scatter, and imparting more enough energy to get out of the star's potential well would require an encounter basically within the planet's surface. This is why we have a moon. Whatever protoplanet was scattering around the early solar system wasn't able to be ejected by Earth, instead crashed into us. Okay, so one of the key features of Roman's upcoming discoveries is that it will probe for the first time low mass planets in a regime where they should dynamically eject things rather than run into them. So on the spot here, I've marked in this dashed line the locus of mass and separation, where you would expect planets to have a Safronov number of 1. And so planets sitting above this line will eject things out of the system, whereas below, where all of or the vast majority of exoplanet discoveries to date sit, you expect collisions instead. And this aspect of Roman's discoveries is even more pronounced when you consider the fact that the typical star in our galaxy is more like a third of a solar mass rather than a solar mass. So just to recap, Roman will be measuring the stuff kicked out of planetary systems with its free-floating planet discoveries, and it will also resolve the population that did the kicking. Okay, so I've been talking about how we'll finally figure out whether our own solar system is unusual with these microlensing discoveries, but we actually already know that we're a little bit unusual, at least in one respect, and that is the fact that we have Jupiter. So we already know from long-term radial velocity monitoring, and this is corroborated by ground-based microlensing surveys, that giant Jupiter mass planets beyond about 1 AU are relatively rare around sun-like stars, found around about something like 10% of sun-like stars, and that occurrence rate goes down as you go to lower mass M-dwarf stars, which are much more numerous. And so Jupiter played a big role in this production of a free-floating planet in the scenario in early solar systems evolution. It rather efficiently ejects this extra ice giant basically in just one close encounter. However, more typical systems won't have such a giant planet around to efficiently eject things out of the system. They'll be comprised of presumably lower mass planets, say something like a bunch of Neptune mass planets. And so one might expect that without a giant planet to very efficiently eject things out of the system, this sort of ejection and production of free-floating planets can take longer. And you'd be right. And it's perhaps surprising just how long it can take. So this is a numerical simulation showing an example system where I've just set up 5 Neptune mass planets on nearly circular and coplanar orbits initially. Again, I'm plotting semi-major axes as solid lines, and then the pericenter, apocenter distances are the sort of shaded regions. So it's the radial extent of each orbit. And I've set the system up in such a way that it goes unstable after a few tens of millions of years, after which it enters this prolonged scattering phase. And one planet gets kicked in, absorbing most of the initial binding energy, while all the other planets are scattered out to hundreds or thousands of AU, but nothing is really ejected for at least 1.5 billion years. And even after 3 billion years of evolution, there's still 3 planets hanging around in the outskirts of the system, sort of scattering stochastically, but still hanging around. And so what you find if you run large batches of these types of simulations is that the dissolution timescale of planetary systems, or in other words, the timescale over which planets are ejected and unbound from the system, is strongly mass dependent. So here I'm summarizing in this plot ensembles of 100 integrations, each where I set things up with 5 planets. And then I'm just recording the average number of bound planets as a function of time for each of these ensembles. The only thing I'm changing in each ensemble is the planet masses. So I'm going from low mass Neptune planets, like the example I just showed in the black curve, all the way up to 30 Neptune mass planets, which is 1.5 Jupiter masses for reference. And you see that the massive systems settle down after about 100 million years or so to a final configuration where there's 2 planets remaining bound and the rest have been ejected, whereas even after billions of years of evolution, the Neptune mass planets are still evolving and scattering planets out. Okay, and so what's more, if you look at where these planets are while they're scattering, they're often much further out than where they started. You saw this already in the example simulation I showed, where the planets are usually around 10 to 100 times further out than where they started. And here I'm showing on the right the cumulative distribution of planet separations after 3 billion years of evolution of the planets that are still remaining bound to the system. I've excluded the inner planet that always gets kicked in and absorbs all the initial binding energy. And so the rest of the planets are generically found roughly between 100 and 1,000 AU for these systems that I started arbitrarily at 10 AU. You can scale things according to whatever you think the starting conditions are, but generically you find that they're about 10 to 100 times further out than where they start. Okay, and so if you put what I've said so far together, namely that many systems won't have massive planets around to efficiently eject things out of the system, so planets can hang around for billions of years, and while they're hanging around, they're often found 10 to 100 times further out from where they started. We predict that a substantial fraction of apparently free-floating planets that'll be found by Roman will actually be widely bound, sort of weakly detached, weakly bound wide orbit planets that haven't been ejected. So microlensing can't actually distinguish between a true free-floating planet and a planet that's a few tens of AU or beyond a few tens of AU from its host star. And this is actually a prediction that can be tested with follow-up observations. And this is something I've been talking to people in the Roman free-floating planet working group about. So what you can do if you observe a microlensing event that looks like a free-floating planet, you can follow up after you observe some magnification event with high-resolution imaging. And if you do that after a few years, the relative proper motion between the background source star and the foreground host of that, what looked like a free-floating planet, will have brought them to a great enough separation that you should be able to resolve the stars in high-resolution imaging. You can also do this with precursor imaging too, if you're lucky enough to have precursor imaging of the field. Okay. So there's another important aspect of the sort of scattering dynamics I've been describing so far, and that is that it can produce very close pericenter passages while this sort of chaotic and violent scattering is going on. If you look at this innermost planet that absorbed all the initial binding energy and got kicked in, you see these periods or bouts of time where it's on highly eccentric orbits so that its pericenter distance is below the axis of the plot. And what you find is that low mass planets in particular are very susceptible to close pericenter passages. So here I'm showing a cumulative histogram of the minimum pericenter distances achieved by planets over the 3 billion year simulations that I ran. And you see that the lowest mass planets can send things into a part in 10 to the 5 AU. You should be screaming at me that they should be falling into their star. And of course, you're right. So this is well within any reasonable host star size. So the simulations that I've run are highly idealized in the sense that none of the bodies have any physical extent, but any real system undergoing this sort of evolution would presumably dump its planets onto the star. What's more, before the planets even get into the star, they could impinge on any sort of additional planets in the system that formed closer in. So here I've marked 0.1 AU as a sort of typical distance at which we find transiting sort of sub-Neptune sized planets, which we know already are abundant around sun-like stars. They're found around something like half of sun-like stars. So this planet-planet scattering dynamics that produces free-floating planets doesn't just shape the outer regions of planetary systems, it has system-wide implications. Okay, so I'll just recap quickly what I've said so far about free-floating planets and how we can use the dynamics of microlensing or dynamics of free-floating planets to use microlensing discoveries to go beyond just basic demographics. So I've emphasized bound and free-floating planet populations should be linked together by the dynamics that produces the free-floating planets in the first place. And I explained that many of the apparent free-floating planets that we observe, because there's not a lot of very large mass giant planets to eject things, should actually be weakly bound detached planets. And finally, I showed that this sort of scattering dynamics doesn't just shape the outer regions of planetary systems, but can have system-wide implications. So maybe I should stop here for questions before I go on to the next part. Yes?
Yeah, so I was wondering how close, how compact need to be these Neptune planetary systems to induce this.
To go unstable, right. So they really just need to be close enough to eventually go unstable. So in the example I showed, right, I set them up in such a way that they went unstable after a few tens of millions of years. If you spread them out a little further, that can take longer. But what you see is that the vast majority of this evolution is just taken up by the sort of scattering dynamics, right? It takes much longer to actually eject things than it did for them to go unstable. And so as long as they're not sort of starting out with separations that leave them stable for billions of years, then it's the scattering dynamics that will really dominate the evolution. And if planet formation is sufficiently efficient that it sort of produces as many planets as a system can support stably initially, then it's pretty reasonable to expect planets to emerge from the protoplanetary disk with dynamical lifetimes on the order of, say, 10 million years, which is similar to the lifetime of the disk, right? Otherwise, it sort of takes a conspiracy for the protoplanetary disk phase to produce a system that just happens to have a sort of multi-billion year instability timescale. Yeah, and so we know these instabilities are happening already, right? Because we see free-floating planets. Yeah, as long as there's not some conspiracy of initial configurations that leave them stable for billions of years, then it doesn't really matter. And yeah, they quickly forget exactly how they started out. Mm-hmm.
Right. So the idea of being able to follow up on the free-floating planets to recognize the host star is very intriguing. I'm wondering if you can't do something more immediate. If I superimpose two stars, and so I'm going to see a blend, and I don't know what the joint function is of lens star versus.
Yeah, I had this exact same question for the observer people, and
but
yeah,
you're going to get something which will be spectrally blended or have an unusual luminosity for the presumed distance. There may be ways to recognize that rather quickly in some cases.
Yeah, so I had this exact same thought, and I was like, why doesn't this work? Why can't you just do it immediately? And so the issue for typical Raman detections is that they'll be too faint to get good spectroscopy, I think. And so, right, if you want to do this spectroscopically anyway, they're usually too faint.
Got JWST up there.
Yeah, that's true. I guess that's up to the JWST tech. Yeah, so that was the explanation I was given by observers who think more about that stuff than me. But yeah, that's a good point that maybe you could do it with JWST. I saw another question back there. Yeah.
Oh, so I have a follow-up question on the initial configuration. Maybe you could take into account the mean motion resonance, like the resonance capture of these planets?
Yeah, so some people believe that disk migration should generically cause systems to emerge in sort of resonant chains. I mean, the short answer is that once they start scattering like this, it really doesn't matter. They'll sort of quickly forget whatever initial configuration they were in. So just any initial configuration that's unstable, as long as it's not unstable on sort of timescales similar to the timescales of this scattering, won't really make a difference to the ultimate outcome. Okay.
Sam,
yes.
Can I ask a question?
Yeah.
Is there anything you can think of that would squelch all of this scattering?
I could think of things that can partially squelch the scattering. for one, throwing a planet into the star. If you look where this one is, right, most of the scattering is probably dominated by encounters with this inner one. That's the one that everybody's consistently sort of coming back into orbit and seeing again. And so if you dump it onto the star, there's sort of nothing left around for them to encounter very frequently. But that would just leave them stranded out at large distances. It would still look like free-floating planets. You would just predict that even more of the free-floating planet population is actually bound.
There might be an angular momentum problem with that, because you're starting out with some angular momentum there, at tens of AU.
Yeah, so they're trading angular momentum. I mean, what's causing these pericenter dips is fundamentally just the long-term transfer of angular momentum between these things out here and this thing, and they sort of trade back and forth. And so they have no problem sort of getting things onto the star. I've thought about, in terms of squelching scattering, if there's a very massive population of planetesimals around to provide dynamical friction, that could sort of settle some of this stuff back down. And that's sort of the story that people invoke for getting Neptune and Uranus back in line after the sort of Nice model shakeup. But you still produce some free-floating planets in that case. And so, yeah, interestingly, if there's enough small bodies around to do that, they should themselves, the small bodies should be ejected as well. And so another thing that sort of gives us a handle on that is interstellar objects. So if those are sort of absorbing all the energy and getting kicked out themselves, then hopefully LSST will tell us lots of interstellar object detections. Okay. Good. So that brings me to part number 2 on understanding the scattering dynamics that I've been describing a little better. And so hopefully the numerical experiments I've shown illustrate the sort of importance of getting a handle on these dynamics that produce free-floating planets for making the best use of upcoming microlensing discoveries. But I want to emphasize that sort of theoretical insights are desperately needed if we really want to do this at scale. The sort of simulations I've been showing can and do take months of CPU time to run. You can't get around this with parallelization. That's sort of the nature of n-body problems. And these sorts of highly eccentric close encounter orbits are really a numericist nightmare. And they're just not going to cut it for the sort of vast parameter space that we need to be able to explore in order to take microlensing detections and try to work our way back to the things we care about, like the initial number of planets and their masses and initial separations. So fortunately, I would say we already have a bit of a foot in the door in terms of understanding this type of scattering dynamics. And this is based on some recent work I did with Scott Tremaine on understanding the scattering dynamics of bodies on highly eccentric orbits. So we looked at an admittedly somewhat simpler model system where you consider just a test particle on a highly eccentric orbit subject to perturbations from a planetary mass perturber on a relatively circular orbit. And so the key idea is to, instead of following the full dynamical evolution over the very long orbit of this highly eccentric large semi-major axis test particle, where it spends most of its time very far away from the planet, where its perturbations are totally unimportant, what you can do instead is just look at how its orbit changes each time it swings through pericenter. And this allows you to follow its dynamics by mapping from pericenter passage to pericenter passage, or one orbital period at a time of the outer body. And so a little bit more detail, the way this works is that you can consider the test particle, because it's so eccentric, you can consider it to basically be on a parabolic orbit. And you can ask, what sort of energy change do I expect the orbit to get as it swings through pericenter on this nearly parabolic orbit? And that's just going to depend on two things. It's going to depend on the pericenter distance that it comes to, and it's going to depend on the orbital phase that the planet is residing at when it reaches pericenter. And so you can write that up as the new orbital energy. So this x is just some scaled version of the binding energy, is going to be equal to the old one plus some change, which is just going to scale like the mass of the planet perturber relative, planetary mass perturber relative to the star, and some function of this angle, as well as the pericenter distance. And I should emphasize the pericenter distance is essentially going to remain fixed with each encounter. This is effectively a consequence of conservation of angular momentum and energy. And so once the particle leaves on its new orbit, it has a new binding energy, which means a new semi-major axis, which means a new orbital period. And so we know how long it's going to take to return to pericenter based on Kepler's law. And that means we also know that what the perturber's orbital phase is going to be the next time it returns to pericenter. It's just going to advance by its orbital frequency multiplied by that period. And so we can predict this theta prime, the next phase of the perturber, the next time the particle swings through pericenter. And so you can put these two pieces together and describe the orbital evolution of a scattering eccentric particle with a sort of iterable map. So in other words, you know what the binding energy and this orbital phase at the next encounter is going to be purely as a function of what they were the last time it went through pericenter. Of course, all the magic is contained in this function here. I won't torture you with the details. I'll just show what this looks like. So this is what the so-called kick function looks like for different pericenter distances for a perturber put at 30 AU, so with Neptune in mind, for instance. And as you expect, as your pericenter distance brings you closer to the perturber, you get bigger kicks since you're swinging closer or having stronger encounters. Okay, so this iterable map gives us a much more efficient way to follow the orbits of highly eccentric particles. So here I'm just showing a head-to-head comparison of this sort of iterable mapping method with direct in-body simulation. So what I'm showing on the left is a whole bunch of test particle trajectories integrated with direct in-body simulations. Each color or set of colored points on this plot is an individual particle trajectory, and all I do is I record it's the particle's instantaneous period relative to the perturber, or Neptune in this case, and the orbital phase of Neptune when it swings through pericenter. There's all sorts of intricate detail in this plot that I could spend a very long time telling you about, but the basic upshot is that you can follow these same trajectories with the map at a small fraction of the overall computational cost, and you get pretty great agreement. Oh, I said these were parameters for this phone number of a TNO, just for reference. This does apply for outer solar system bodies as well. Okay, so that's great. So we have this more efficient way of describing individual particle trajectories. But we can go even further and develop an overall sort of statistical description of bodies. You saw how sort of chaotic the scattering was that I showed earlier in the simulations. These sorts of test particles are subject to very chaotic evolution that leads to basically diffusion in their orbital binding energy, or equivalently their semi-major axes. And any sort of diffusion process is just described by a diffusion coefficient. And you can work out to varying levels of approximation a description for this diffusion. The simplest assumption is just that repeated encounters happen at essentially random phases. And so if you make that assumption, you find that the diffusion rate depends on the mass ratio of the perturber relative to the star squared. And then you can compute the phase average of this kick function. So the upshot is that you have an analytic description of orbital evolution in terms of the diffusion process, or basically a random walk rather than following trajectories. Okay, and this sort of diffusive approximation provides a pretty nice description of what you see in direct in-body simulations. So in this panel of or series of histograms here, I'm showing a comparison of sort of diffusive evolution of these particles on highly eccentric orbits with in-body shown by the black histograms over time, and then compared to this map in the cyan histograms, and then which is a few hundred times faster than in-body. And then you can also just solve 1D diffusion equations, which is a few seconds on a laptop at most. And you see you get a great description of the orbital evolution. Okay, so I've described a little bit about how you can understand the sort of scattering dynamics that's responsible for producing free-floating planets using this sort of mapping approach. And I finally, before I conclude, just want to close with a few thoughts about our own solar system's production of free-floating planets. So I mentioned earlier that people think that perhaps initially in the early solar system's evolution that we kicked out another ice giant planet. But more generally, we have a sort of dynamical record of the early solar system's evolution, sort of ingrained in the distribution of orbital properties of small bodies in the outer solar system. And in the next few years, we should actually be getting this over an order of magnitude increase in the number of so-called trans-Neptunian objects. So here I'm just showing what they look like in space. You see those earlier sort of disk-like structure, referred to as the Kuiper belt, but we also find these things on highly eccentric orbits. And as I mentioned, these trans-Neptunian objects basically serve as a record of our own outer solar system's evolution. There's all sorts of intricate dynamical structure that one sees in their orbital distributions. So this is illustrated nicely in this plot from a review from Brett Glabman and Kat Volk a few years ago. And usually what's done is the trans-Neptunian objects are divided up into these various classes. And one of the most prominent things you see in this are these resonant objects. So these are bodies that sit at orbital locations where their orbital period is in a resonant or is in an integer ratio multiple of Neptune's period. The most famous one is probably Pluto, which sits in this collection of bodies at the 3:2 resonance. But there's other bodies there as well, and there's resonances populated sort of all the way out. And these, together with the scattered and detached objects, which I'll return to in a minute, are taken as part of the evidence supporting our solar system undergoing an early instability and possibly producing free-floating planets. And the argument is something like this. So these resonant bodies that you see are naturally sort of swept up into those configurations if Neptune underwent some migration early during the solar system's evolution. So I'm showing here a highly simplified simulation where all I've done is stuck in Neptune, caused it to migrate outward by some fictitious forces I'm adding in addition to the in-body simulation. And I've added this sort of initial population of test particles. And you can see that as Neptune migrates out, it sweeps up these bodies into its resonances. You can ask Manu all about this, of course. Yeah, so that this feature sort of reproduces these resonant bodies we see here and is thought to be caused by this sort of Nice model that's designed to explain the structure we see in the outer solar system. So the basic picture is that, as I said earlier, the giant planets are thought to start in an initially more compact configuration. They develop some orbital instability, scattering the planets we know about and possibly additional planets as well. As a result of that scattering, Neptune and Uranus get thrown onto highly eccentric orbits. And then due to continued scattering, I think I lost a slide, but anyway, due to continued scattering, this is what causes Neptune's outward migration, causing it to sweep those bodies up in the resonances that you see. But also, as a part of this instability, you produce these bodies on highly eccentric orbits with their pericenters coming back close to Neptune. So this is sort of a product of the scattering process. And one of the sort of prevailing mysteries of these bodies on highly eccentric orbits is the so-called detached population. These are the bodies that are shown in yellow, where they're on highly eccentric orbits that look like they've undergone scattering in the past, but if you look in detail where they sit, they no longer undergo scattering due to their interactions with Neptune. And so it's hard to explain how they got there as a result of interactions with Neptune if they're no longer strongly interacting with Neptune. Basically, if they should be able to get there by interactions with Neptune, they should be able to get out of that location. So this is a quite busy plot from that work I was describing earlier with Scott. But if you just pay attention to this orange line here in semi-major axis versus perihelion distance, it separates bodies that should undergo scattering in this sort of chaotic diffusive evolution. So you see lots of TNOs sort of down here, but these will evolve over the course of the solar system. But there's also these things are at wide semi-major axes, but that don't undergo scattering due to Neptune. And so it's hard to place them on those orbits unless you have additional bodies to interact them with. And so one of the ideas that's emerged is that if the solar system was producing free-floating planets, in other words, if it was scattering out planetary mass objects over the course of this evolution, while those planetary mass objects are still undergoing this slow sort of outward scattering process, their own dynamical influence can lift the pericenter distances of some of those bodies and then place them in this sort of detached region. So this is a simulation taken from some recent work by Yukon Huang, illustrating this effect. So they're simulating the solar system plus an additional two Earth mass planet, which they've placed initially with a pericenter distance of 40 AU and a semi-major axis of 300 AU. And you can see that it lifted over the course of this animation, it lifted pericenters up out of the region where they would be susceptible to Neptune. And then eventually this rogue planet gets scattered all the way out of the solar system to become a free-floating planet. Okay, so that brings me to my conclusions. So I've told you about how microlensing will be probing solar system-like scales for the first time, and how we can go beyond just the demographic data we're going to get from these discoveries and hopefully say something about how these systems initially formed and have since evolved by leveraging free-floating planets. I talked a little bit about how we can better understand the sort of scattering dynamics that's ultimately responsible for producing free-floating planets. And then I touched a little bit on how planetary mass objects ejected from our own solar system have shaped the population of TNOs. So I'll leave it there.
Time for questions.
Yes.
Pardon me if I missed this. Let's say you may put this together in your last simulation that you showed, but so you're talking about raising the little planetesimals
Yep.
to make detached orbits, but you're doing that something on the way out of the solar system.
Yep.
And so, what does it take to explain our population of detached objects? Is there something that you one or two of these, over the age of the solar system, or
Yeah.
boatload of them to get what you see? And does that can you
Probably, yeah. So probably with too many of them, you're not left with a sort of net direction to torque things and raise their pericenter distances. Well, I'll say first that it's probably a very underexplored problem at present, and part of the difficulty is that we don't have great information about the pericenter distribution, say, of these detached objects. They're sort of been at the hairy edge of what we've been able to detect, but hopefully with LSST, we should be getting lots more and be able to say something. So how many free-floating planets do you actually need to raise these up? Well, so one thing that determines timescales here is the mass of whatever you're scattering. And so with something, you need something sufficiently massive so that the timescale is basically proportional to the mass. And so in that simulation, that was like 100 million year simulation. And so, you can scale up or down according to that. If you make it too massive, it would probably make a mess of the cold classical belt. And so you want to avoid that. If it's too low mass, so one issue here is, right, it's hanging around for so long because it's basically just coupled to Neptune. I said that Jupiter makes quick work of anything, but what you really need is something that's basically just being scattered by Neptune, and that takes a long time to scatter stuff out, and so it hangs around for a long time and is able to do this. So a few Earth masses is probably the sweet spot, but
it'd be great if you could invert this, and be able to actually estimate that.
Yeah. I mean, so one thing I guess that'll be interesting coming out as well with free floating planet detections is what is the actual mass function of stuff that's ejected. What people have done so far is what every physicist do in the absence of data is fit a power law. And so, right. So we have our power law fit, and it says that there should be lots of Earth mass things around. So it's not super surprising. It's probably expected that the solar system ejected at least one or a few of these things. Yeah, we'll have a chance to compare it to other systems. Yes.
With the slide that had the comparison between the 2-point Cray maps, one made with full integrations and the other with this mapping, do you have a GitHub page that would have sample code to reproduce?
Yes-ish. If I have to remember what's on the GitHub, it is implemented in the CellMech code that Renu mentioned. So it is at least out there. I can't recall. The thing about managing a large project is you forget how user-friendly you've made every little piece of it. But if it's not, if what you find is not user-friendly enough, you are more than welcome to email me.
Okay, thank you.
Yeah, so it's fully implemented in CellMech, that is mapping.
So the long lost ice giant sibling, is that related to Planet 9?
Yeah, so one of the problems with it being Planet 9 and not long lost is how do you get it to stop on its way out? So, if we had another ice giant mass planet that got scattered out, it should just keep on its way out. It should basically keep coming back to the same pericenter distance, which means it'll keep scattering off the other giant planets, which means it's sort of hard to get stuck out in the outer solar system. But we should know soon enough again with LSST, I guess. Yes.
How do close stellar passages affect the story?
Yeah, so people have certainly simulated, say, like planetary systems in a birth cluster with stars, and they look at flybys. And the short answer is that they're usually a pretty minor effect for typical planetary separations. You might think, once you get this scattering going, you're kicking things out to, say, thousands of AU, where they would nominally be more susceptible to flybys, especially early in the history. But there you run into the difficulty of whether or not you can get them out to those distances in time while you're still in the birth cluster and you're likely to have flybys. And for the case of the Neptune mass planets I showed, the answer is that you probably can't. They probably take too long to get out there. They're not out there until maybe like 100 mega years or something, which is, I think, kind of pushing it for being still in your birth environment. Yep. So they probably make a contribution, but it doesn't seem to make a huge difference, at least based on what we know so far.
If there are no other questions, we can thank Sam again.